Good evening, everyone. First of all, I hope everyone is staying safe, and I know that everyone's okay. Thanks for sharing your evening with us here. I'm very proud to be presenting for the microservices meetup. So my talk today is going to be about Kafka Streams and how we leveraged Kafka Streams in my company to build a few event-driven microservices. So my name is Stathis. I'm a lead software engineer for ThousandEyes. I'm a member of the backend team. And by the way, also ThousandEyes was acquired by Cisco a couple months ago. So I guess happy days. Today, we're going to begin with like a small overview of what Kafka is, a very high-level overview. Then we're going to discuss a little bit about Kafka Streams and why we chose Kafka Streams over other solutions. Then I'm going to give you I'm going to say a few words about the Endpoint Agent, which is the product I'm currently working on, so that you can have a little bit of context. And then we're going to dive into the various microservices that we built using Kafka Streams. Then I'm going to share you some production issues that we faced and how we resolved them. We're going to talk about some takeaways at the end, and then we'll have time for some Q&A if you have a question for me. So in the beginning, when you're building a system, everything is very simple. You have a source system, which can be your web application, and you have your database, can be a target system, and you're just writing to that. But as your product grows, you start having more applications, more microservices, more databases. You might have external analytics systems. You might want to consume a stream of events from logs or from wherever other source you want. And that creates all those dependencies between the systems, and they all need to know how to talk to each other. So Kafka can come in the middle, and it can decouple those systems. So now systems, they can talk to Kafka, and also the target systems, they can consume from Kafka. So it's much simpler to build systems like that. So Kafka was created, of course, by LinkedIn. Probably all of you already know those things, but it was created by LinkedIn. It is open source now and maintained by Confluent. It's distributed, and it's very resilient in faults. You can scale it horizontally in commodity hardware. You can scale it to hundreds of brokers and consume millions, probably billions of messages. It has great performance, and it's a safe bet, in my opinion. It's used by many famous companies like Netflix, Airbnb, and as we said, it was created by LinkedIn also. So again, Apache Kafka can be used as a messaging system, as, for example, an activity tracking tool. You can gather metrics from various systems. You can gather all your application logs, for example, into Kafka. You can use it for stream processing, which we're going to be discussing about today. And it works really well with many famous big data technologies like Spark, Flink, Hadoop, and others. So today we're going to mainly be covering Kafka Streams, I guess. So what is Kafka Streams, right? Kafka Streams is a simple library, not a simple, basically it's a library that you can embed inside your Java code. So let's say you have a Quarkus app or a Micronaut app or a Spring Boot app. You can embed that inside your application, and you can consume from Kafka and produce into it and transform those messages in any way you like. Of course, it inherits all the properties of Kafka. So it's highly scalable, it's elastic, it can tolerate faults. It was one of the first libraries to support exactly one's capabilities, which is a great feature. And it can work for any application size, meaning that you can start small. You can have just one node of Kafka Streams, and as you grow, you can scale it very easily using Kafka. So to give a little bit of perspective, this is an architectural diagram of where Kafka Streams fits in. So let's say we have a Kafka cluster, and let's say we have a source system that somehow it pushes things into Kafka, and then Kafka Streams is on the right side, so it consumes and produces inside Kafka. And it was created in 2016. It was part of Kafka 0.10, and it's considered a serious contender to other processing frameworks like Spark, Flink, or Apache Nifi. So the product I'm working on, right? So the product I'm working on is called the Endpoint Agent, and basically what it is, it's a small program that you install in your laptop or your desktop or PC. Well, we don't directly sell to you specifically, we sell to companies. So companies, your employer, for example, will pay us and he will install in your laptops, amongst the other things you have installed in your laptops from your company, you will also have the Endpoint Agent installed. And this agent will try to talk to the network and collect various network metrics like trace routes or outputs from ping. And we collect all that and we send them to our backend for processing. We also support understanding your employees' experience while they're browsing the web. So we also collect some metadata from the browser by an additional plugin that you can install if you want. An interesting thing about the Endpoint Agent that we're going to be using later, so I'm going to mention it now, is that it continuously checks in with the backend by sending some interesting stuff about its state. And we support our views. They're very easy to use. We support lots of filters on our views. You can drill down to every detail. You can filter by agent or by the Wi-Fi network that your agent is in or the specific network that it's in. And that, on top of the data, we support also alerts and various reports that you might want to extract from your data set. So this is the also a high-level architecture overview of our data pipeline. So on the left side, we have all those endpoint agents that they're submitting to our microservices. They're behind, of course, a load balancer. So we run everything in Kubernetes. We rely heavily in Kafka. So we push data points to Kafka, we enrich them, and then we push them to Kafka again, and afterwards they end up either in MongoDB or Elasticsearch, because we use it for our views. For some queries, Elasticsearch gives us much better performance. For other queries, MongoDB is better. Although I guess we're in the process of kind of removing MongoDB these days, but we still have it. And other systems like the alerter, for example, that needs to alert on top of data points will consume our data points from Kafka. So Kafka is a very central part of our architecture. So why did we want to build these types of Kafka Stream services that are event-driven? So for us, it's very important that the endpoint agent scales from very small. When we started 4 years ago, it was probably 100 or 200 agents, and now we are approaching the 100K mark. So we want to be able to, for our backend to scale easily. And for us, it's very important to respond to events and be as real time as possible. So when something happens on the agent, we want to immediately know that and do something with that, schedule specific tests to it, or do various other interesting works, or correlate events. And in general, the communication between the agent and the backend is much optimal being asynchronous than asynchronous, because it's not like a customer talking to a CRUD API. So between systems, you can have asynchronous communication, and it can feel much easier to work with. So for us, Kafka Streams is very important because it supports various interesting things like you can aggregate on top of your data and emit those aggregated data and do something with that. We also use the windowing operations from Kafka Streams. And we really like the K-tables and that Kafka Streams supports out of the box. So I'm going to begin with our first use case, which was the schedule tests. And so basically what we want to do in this use case was to basically dynamically being able to schedule synthetic tests, or imagine like schedule a ping to run from a specific agent. So that's what we call a schedule test in schedule test in our product. It's basically, as I said, a synthetic test, and you specify the interval that you want this to run, and you also specify to which agents you want this to run. And then the agents, they kind of pick up this configuration, and then they start submitting all those data points to the backend. And then we visualize that, as I showed earlier. When we first had to solve this problem, we went with the most basic approach. So we developed what we called back then a batch job that would do this scheduling for us. So I mentioned again that agents check in with the backend every 10 minutes. So we had a batch job that would run every 15 minutes. It would get all that state from various places. We had stuff in MongoDB, we had stuff in MySQL, we have stuff in Redis. So it would fetch all that state from various places. It would try to run this scheduling logic on top of all that data, and then it would emit a list of assignments that then would somehow end up inside the agent, and the agent would then schedule those tests, which are, I said, pings or trace routes, and then would send them back to the backend. But this approach didn't work very well for us. We did stress test it, and we noticed that there was no easy way to scale it. We could only scale it horizontally. We couldn't scale it in various machines by adding more machines. So it wasn't that great. And as we were adding more agents, the latency increased for the scheduling job. So we had to find a different solution. So we kind of changed our approach by taking all those check-ins that the agent is doing every 10 minutes and actually putting them into Kafka. So in that case, we created a stream of agent check-ins, and we used that stream of agent check-ins through Kafka Streams to power an application that we call the Scheduler, which is a Kafka Streams application, which kind of is able to run that business logic and emit a list of assignments. Actually, it stores them in Kafka. And the cool thing about this application is that because it's based on the Kafka partitioning model, as you add more partitions to your application, basically, you can scale it even more if you ever hit a limit. For example, now, I think we have around 32 partitions, something like that, and it's working fine for us for 100K agents. So it's doing pretty good. And this is the architecture a little bit of the Kafka Streams application. So basically, I mentioned before that we had this application state or customer state that we needed to fetch inside the batch job, but in the Kafka Streams application, this is done in a different way. So by polling that state and putting it into Kafka, we are able to create what Kafka Streams calls global K-tables. And those global K-tables, they can live in all Kafka Streams instances. So whenever a check-in arrives from the agent, we're able to accumulate that state by joining that state of the customer, which is the tests or which is whatever else is needed to take a decision for scheduling. Then we run that logic, and then we emit and save into Kafka the list of assignments. The cool thing again about this application is that all state lives in Kafka. So basically that all state lives in Kafka. It was built with at least once delivery in mind, because when we first built this, they hadn't yet released the exactly one, so it was a long time ago, I guess. But we also use materialized views. So from Kafka, we have a separate process that might consume those assignments and put them into MongoDB. And this is crucial for us for displaying historical data or doing historical queries to see, at a specific point in time, which agents were assigned to which test. So I mentioned that all the state for the tests that are assigned to the agent lives inside Kafka, and we use another feature from Kafka Stream, which is called interactive queries. And with interactive queries, you're able to query this in memory, this state of the K table that has the assignments, and you can provide the REST API on top of that. And it's super fast. And it's working great for us. Of course, one small problem we had, for example, was that when we were deploying that service, the agents would throw 500s because they couldn't access their state. So for those cases, we kind of circumvent that and we go to MongoDB temporarily to get that state until the scheduler is back up. So now we're moving on to the second application, which we call the check-in reconciler. And basically, this is a sidekick application to the scheduler, because what it will try to do is that it will try to make the scheduler aware of other types of events. So now the scheduler only knows about agent check-ins and nothing else. The thing is that a customer can change a test. So if they change the test, then this means that probably the business logic behind the scheduling algorithm must change. So the scheduling must run again. So this is what check-in reconciler tries to do. And it looks like this. So basically, again, it consumes from the list of check-ins. Then it will do repartitioning by account or customer, let's say, so that it can accumulate all the check-ins that are active in the system. So meaning at this instant, we have, for example, 10,000 agents, and that 10,000 agents, they have a mapping to a check-in, and that check-in, we store it into a K table. So, and that K table, we basically use it from another Kafka Streams application, which reacts on application events, like when a test changes or when something else changes inside the application. And we are able to join with that state, so with that list of check-ins, and then we are able to send that as an input to the scheduler again, so that the scheduler can reevaluate all the assignments and emit different assignments for the agent. Sorry. Everything was okay with this application until, I guess, we reached a first bottleneck. So when we reached the 20K agents, we started seeing that mostly the topics that are backing up the K tables, we were producing lots of data to it. So basically, the problem here was that we were updating the K table on every event, which is not great because, as I mentioned here, we are doing a repartitioning. So when a customer, let's say, is more chatty than others, then that specific customer will create more data for you, and all customers that reside on the same partition in Kafka, they will experience late processing. So yeah, we were without really wanting, we were creating hot partitions, which took too long to process. As you can see here, it's not here, but anyway, it took probably a few hours to process the backlog of messages in Kafka. So some customers were behind. As a first temporary solution, we noticed that we weren't creating our K table properly, so we needed to enable our caching mechanism in the K table and also increase the commit interval. So at which intervals, Kafka Streams will commit its internal state into Kafka, so it doesn't all the time try to go to Kafka, and you have then problems like this where you produce so many bytes into the network. And this worked for us, but again, we weren't super happy. So we did another round of stress tests, and we noticed that there wasn't the next breaking point around the corner. So what we did basically was to remove entirely the repartitioning step, because it wasn't a good strategy to go from a very good partition key, which was the agent key, for example, which is a UUID, to an account ID, because we were creating hot partitions, and we removed the partitioning key entirely. And instead, we kind of used this Kafka Streams application. We stored those active check-ins inside Redis. And then again, everything else looks the same. Again, there's similar access patterns to this Kafka Streams application. Nothing changed. The only thing that we moved was the repartitioning, and that we're storing stuff into Redis. And this is working great for us for now too. I think because we have plans to go even larger from 100,000 entities, probably we need to revisit that. But for now, it's been working great for us, and it was pretty easy to implement. Which now leads us to our final application, which is what we call the alert aggregator. And the alert aggregator, basically, it will grab one of our data pipelines. So we have various data pipelines in the Endpoint Agent. One of them is what we call the real user monitoring data pipeline. So when you browse the web, we collect those events from specific pages that your employee is visiting, and then we send those to our backend. The thing with those events is that they don't have a specific interval when they happen. It's not like schedule tests. Schedulers happen every 1 minute, every 5 minutes. It depends on your configuration. But our alerter works only with binned data. So it wouldn't work very well with the nature of the real user monitoring events. So we decided that we're going to create this 1 minute window of data and then emit those aggregated metrics into a new topic, and the alerter would consume from that topic. So we went ahead and we created this very simple Kafka Streams application, which has a time window. It aggregates that state into another topic, and then it outputs to a final topic. The problem, though, with this Kafka Streams application is that every time there is an event, Kafka Streams will update the internal, it will emit events downstream all the time, every time there is an event. So that was not good, as you can understand, for an alerting use case, because that means that you would get false alerts, and we don't want that for our customers. So we needed basically to emit an event only when the window closes. So when the 1 minute window closes, plus the grace period that we have configured, then we want to receive the aggregated event. So we dig into the documentation. We found a very nice blog post explaining how they have the suppress operator for exactly this use case. So we added the suppress operator after the aggregation, and this meant that Kafka Streams could buffer all those events and keep them until the time comes for the aggregate event to be submitted downstream. And this worked great, but then from some metrics that we gathered, we noticed that final event, sometimes it would take a long time to arrive. Again, that's not great for an alerting use case. We want exactly on the clock, on the minute, exactly we want to receive the aggregated event, even if data points are not aggregated yet, because they're useless for the alerter, basically. So basically, we noticed that the act of closing a window and emitting a downstream event is also event-driven inside Kafka Streams. So Kafka Streams has the concept of a stream clock, and a stream clock is not the same as the watch you have on your wrist. So it needs events that advance its internal stream clock. So what was happening is that Kafka Streams was expecting for an event that had a bigger timestamp than your aggregation timestamp to emit the downstream event. So we had to find a solution for this. We created a separate cron job that creates like a fake or an empty event, but it has the correct timestamp and is able to advance the internal clock of Kafka Streams, and then it kind of forces Kafka Streams to emit an event to the alerter, and it worked great for us. So we were happy with that. So now I'd like to share with you some production issues we have. Probably it can help some of you or not. So in so we use the lots of K tables and global K tables in Kafka. And by the way, we also used we use a very old version of Kafka. We have plans to migrate to a new one. But in many instances, we found out that compaction wasn't working as we were expecting it to work. So that was probably because we didn't configure it the first time. So you need to configure your compaction, so your Kafka topic segment size, how big do you want them to get, and stuff like that. So we did that, and we kind of made it work. But there were cases where compaction wasn't working, and that led to topics accumulating lots of state, gigabytes of data, and that meant also that some Kafka Streams app would crash because they had to fetch all that data from the network, from Kafka, sorry. And yeah, we found out that compaction didn't run, and then we tried to force it somehow by picking the right values for us, and then it worked. And then when it worked, it was the Kafka Streams apps were loading very fast because it was the state they needed to fetch was much smaller. Again, I think I already mentioned that we had a production issue with the repartitioning because we were repartitioning to a hotkey to the account ID. So be careful when you pick your partition keys and try to avoid hotkeys if possible. Another interesting issue we had was with interactive queries. Actually, this happened only once and a long time ago. But at some point, we had implemented this REST layer on top of interactive queries. And actually, we were querying that service, the scheduler, to get that list of assignments. So what was happening is that when the request was received from the scheduler, then the scheduler would look at the Kafka Streams metadata, and it would ask Kafka Streams, where is this specific key, right? And Kafka Streams would tell our code that it is on the other instance, and we would go to the other instance. But the other instance also thought that the key was in the previous instance. So we kind of created this circle. We don't know exactly what caused it. It only happened once, but we basically saw that here the production issue basically was a combination of things because we didn't have proper timeouts, and as this circle was being created, the thread pool was getting exhausted, the threads were not getting released, so the services appeared as dead, and agents would receive 500s. But we circumvented that by making sure that we never do more than one hop. So we pass the state along with the REST API request, and we only try to make only one hop, so this situation never happens. But it hasn't never happened to us again after that instant. And some key takeaways from all this journey. When you're using Ktable, make sure that you use the cache and you configure your commit interval for the application. It can help a lot, especially if you are receiving lots and lots of traffic. For example, for our case, everything was working fine without it, but when we had way less agents. So yeah, when we reach more, it just would come back and bite us. Again, I cannot stress this enough. The partition key is very important. I made this mistake multiple times also, so that's why probably I'm putting in the key takeaways. Be careful with your partition keys, especially when you have lots of traffic, right? Always put some alerts and look at the graphs for your growth of your topics, especially if they're compacted ones. Make sure that you have configured compaction properly. So yeah, so another a very interesting thing that yeah, I guess we could have known better in the beginning, but we did all our Kafka topics using JSON, and it's not that JSON is bad because it helps a lot in when we are consuming from Kafka, we can see, we can read it. It's very easy for debugging. But if I would do it again, I would probably go with a binary format, just because of all that byte saving you can do compared to JSON. So if you can use a binary format, this comes with downsides, right? Also, when you need to debug something, so trade-offs. So in my opinion, also using Kafka as a database is very possible. Everything to do that is there, but from my experience, don't overdo it. I mean, I demonstrated that in this very specific application, the scheduler. We kind of did that. We used it as a database, and it is pretty cool. But just, I guess, don't overdo it. And something that always I put as a reminder for myself is that small latencies in your processor, they can really add up when you have a huge backlog of messages to consume. So even if your processor needs 100 milliseconds to do something, if you have a backlog of 10,000 messages to process, then this takes 16 minutes, and maybe that's not great for a live system. It really depends on your use case. Yep, and I guess that was it. That was me. All these are written in a blog post in the ThousandEyes Medium blog platform, if you're interested. And yeah, that's it. Thank you very much.
Thank you, Stathis. There are a few questions before we let you go. Cool. I'm going to read them out so that they are recorded. One record at a time. Does it have any performance implications? If it does not support batch.
For Kafka Streams, performance implications. I haven't seen any performance implications. Yeah, it's also very general, the question, so I cannot directly answer. Again, just try to use a good partition key, and probably you won't see a performance implication.
Yeah, I guess the question is, given that you're consuming one record at a time, does it have performance implications versus consuming?
Yeah, I guess it depends on what you're trying to do, right? If you're trying to write to MongoDB, it would be best to do it in batches rather than one by one. It really depends.
Cool. Next question. Do you recommend to use Kafka for a request response model?
No, I wouldn't recommend that, and I always advised against that. I'm not saying that it's not doable. I think that it's way harder to do than a simple Spring Boot application with a REST API that talks to a database.
I guess there are some use cases where you could use Kafka, like if you use CQRS or any. Actually, Demos is going to talk about some of these things in the next talk, but I think there are some use cases where this could be quite powerful. But I agree, it's additional moving parts, which makes things more complex, and sometimes that's not necessary.
Yeah. It depends on many things, right? Maybe if you wanna how eventual consistent you wanna be, and what things your application needs to do. Yeah.
Yeah. Cool. Next question. Could you explain what exactly are hotkeys?
Yes. So yeah, I call them hotkeys. Basically, is in Kafka we have partitions, right? And then you provide the key, and the key. Usually you will pick in which partition it will go. So by default, I think Murmur has algorithm is being used modulo the number of topics you have. So you pick one of the topics. So if lots of your traffic ends up in one partition, that means you have a hot partition, basically. Basically, that's it. And this can happen, for example, when you pick one partition key that is very chatty, like as I mentioned the account ID. The account ID, if an account has 100,000 agents, then if I'm repartitioning by account ID, all the data from 100,000 agents will end up in the same partition. So that's a hotkey, and you don't want to do that. You want to be able to spread your load in many partitions.
Can we use AVRO instead of binary or JSON to help us review the data in case, if required?
Yeah, of course you can use AVRO. I think AVRO, if I'm not mistaken, can be a little bit more wasteful than JSON, but yeah, I'm not 100% sure. Also, AVRO supports binary, so I don't know, maybe you can start with AVRO and start producing with the human readable format and then use the binary format from AVRO. Maybe that's doable, I think.
How do you decide the number of partitions required? This is a great question. What factors to be considered?
That's a very good question. That's a very good question. Actually, I think what you have to do is you have to know your cluster and your hardware, right? So you need to run stress tests and understand how much performance you can get out of one partition. And then you can say, oh, look, I can have this many requests per second in this partition, this many requests per second out, or something like that. And then just understand for your system how many events per second do you want to support, and then multiply by the number of partitions you will end up using. I think that's a legit way of deciding that. And there's a very good blog post I might share it later about figuring out how many partitions to use in Confluent, I think.
If I can add to that, I think that's a very good answer. But one of the things that we did with Kafka where I work is we just started by the default of 3 partitions. Just because like you often do 3 because usually you have 3 availability zones, and so 3 is usually a number that you use. Like if you have a service that doesn't have that much traffic, usually you have like 3 replicas of that, and usually that works well, then you can scale it up. But the problem with having 3 partitions is that you can only have 3 pods or services consuming from those partitions. So if you have, I don't know, 15 partitions, you can have 1 service consuming 5 of them. 3 services consuming 5 each, and that way you get 15. And then if you need to scale up, then you can add services, and you can add up to 15 services because you have 15 partitions. So you always have to remember you can only have 1 thing consuming from a partition for each consumer group. You can have multiple consumer groups, but usually if you have a different consumer group, it means they do different things. So that's something to keep in mind. And then when I did my research to work out, okay, what's the number that I should use? The reason really a downside in having a big number of partitions, of course, the performance is the main thing that you should look at, like Stathis said. But I know of banks that use like 192 different partitions, and they have no problems with that.
Yeah, we use 128, and it's with only 4 brokers, and it's working fine. But I think also the hardware is very important, because if you don't have good hardware and you try to put too much, it won't work very well. So yeah. Anyway.
What was your use case for using a global K-table?
Yeah, so for global K-tables, we were storing customer metadata. And with global K-tables, a copy of a global K-table will live in every instance. So if you scale to 100 microservices, each of them will have all the states from the global K-table. So that's why we used it. Because then also I mentioned that we had events that would arrive in the Kafka Streams app, and then this would need that data immediately. So it was a very easy way to have that data where the processing is located. So you could have the event; it will immediately get the state for the metadata from the global K-table to the business logic, and then do something else. The alternative would be to use a K-table, for example. But if you want to use a K-table and join between K-tables, you have to collocate data with the same partition key. And when you have account data, you cannot. We had an agent ID and account data, so account data couldn't be collocated with agent ID. So that's why we use global KDB mainly.
Cool. How is the reliability? Can we lose data when using cache if something goes wrong before commit?
I think that's a good question. I think what happens is that when the application restarts, it starts again from the previous commit. So yeah, maybe you are near the end of your processing. Basically, when you restart, everything will begin like from the previous checkpoint in Kafka. So you don't really lose data.
If you're planning on materializing that data, you have to worry about duplicating. Like if you do a bunch of work and then it dies before it moves the offset, then when it restarts again from that, you need to make sure that you're not processing the same thing twice, right?
That's a good thing, but from when I'm materializing in Mongo, I materialize by ID, which I have already generated. So I'm upserting. Yeah, I didn't mention that.
But like you could do things like send an email and then you would send it twice in that situation.
Yeah, that's not great. Yeah, definitely. So in that case, you wouldn't go with a big commit interval. I think you would try to commit at small intervals.
Yeah. What do you think about use Kafka to decouple an application in a request response mode to mitigate the asynchronous behavior and the necessity to load the latency, the request and backend response? Is it recommended? I mean, between client request and backend response.
Not sure I follow exactly about Kafka application. Yeah, I don't really understand the question exactly. Maybe.
Yeah, me neither.
Yeah. No worries.
Don't worry about it. Maybe you can send a message later on the meetup page.
Yes, you can send to me. It's also late for me. I've been doing migrations all day, so
All right. If there are no more questions, we're gonna take. Okay, we have one more. So presumably you have use cases which are in Kafka, Kafka to Kafka, where K-streams is not appropriate. Are you also using standard producer consumers, and what are the extra considerations there?
Yes, we are using regular producer and Kafka consumer in our pipeline. That's how we build our first Kafka applications. Extra considerations is that we always operated under the mindset of at least once delivery. So we try to make our data stores to deduplicate data, to be our data wants to be idempotent. For example, we don't do retries on our producers. The in-flight, we don't do in-flight retries because that can lead to changing the order of the record that is in flight to be sent to Kafka. So we don't do that. We always try to send one at a time. I'm not prepared for this question. I have many more considerations for these APIs, but I guess I can share later if you want to ask something else.
Cool. Next question. I guess this needs to be the last one because we have to move to the next talk.
Yes.
Having mentioned that you have so many consumers, how do you manage your Kafka offsets to ensure that performance is consistent? Any tips on this?
Kafka Streams, I guess my answer here is Kafka Streams manages that for me, and I'm a happier person. I don't have to manage it. But I know for 5 years ago that we tried to manage offsets ourselves, and we still have some applications that yeah, nobody wants to work on those. So yeah, if possible, just let the library do the management for you. That's what Kafka Streams is for anyway.